So here I am, 70 kilometers outside of Vilnius, Lithuania, with Arnas Drazdauskas, who is an associate professor at Vilnius University and an observational astronomer. We are actually standing on the deck of the walk that encircles a 1.65 meter optical telescope, which is very much in use on the 100 days that it approximately 100 days that it sees clear nights. And Arnas, you are involved in a ongoing campaign to measure the do spectroscopy on bright stars out to about 3,000 light years or 1 kiloparsec, F, G, and K stars. Is that correct?
That's right.
So tell us a little bit about this telescope and your spectrograph here, which you just showed me, which is about the size of what? A small car?
Small, bigger bathtub maybe? Yes, a small car.
I think it's bigger than a bathtub.
Maybe. So the telescope itself is 165 centimeter, and it's one of the largest out there at the north side of the Europe. This is not a perfect place for a telescope, but it's a very convenient one because we can observe targets that are not reachable by other telescopes, for example, in Chile. Yeah, and this telescope is not as interesting to use, so people would use it every day. Let's say Spanish people, they're not as interested in this telescope, but for us it's a perfect opportunity to use it for our own research, our own tasks, and we use it, like you mentioned, basically every clear night.
And you're doing spectroscopy to find out two or three crucial things about these bright stars. Tell us.
Yeah, so spectroscopy is one of the most powerful tools to study the stars. We start by analyzing the spectra and figuring out the stellar atmospheric parameters. So that temperature, surface gravity, metallicity, microturbulence velocity. And when we have those, we can take a deeper look at what's inside the star. Namely chemical abundance of chemical elements, up to 32 species, maybe even more. So starting like with CNO, the elements important for life.
Carbon and oxygen.
Carbon, oxygen, nitrogen, magnesium, silicon, and going as high up as barium or yttrium, those neutron capture elements. They tell us different aspects of the stellar formation and evolution histories.
And you've been doing this here for about 7 years?
The project that we are running is about 7 years, yeah.
And your end goal is to try to get enough data that is statistically significant enough that you can make some sort of correlation between the chemical abundances of the stars and the type planets that they might harbor.
Yes.
And it's counterintuitive, you were telling me on the drive out here, that a lot of these stars have high iron abundances. And it's counterintuitive that stars with high iron abundances create gas-type planets, not necessarily rocky planets like that could harbor Earths or Mars or Venuses, correct?
Yeah, so that's what data shows us, that more metal-rich stars tend to produce more massive planets. However, we have to be careful here because most massive planets are most easiest to detect, and smaller planets are more difficult to detect. So what's to say that we will not detect smaller planets around these stars? So we do find smaller planets around metal-rich stars. Yes, we do. But this tendency is mostly towards attributed to giants. Giants are most common to find around more metal-rich stars.
You mean the gas giants?
Yeah, the gas giants like Jupiters or Neptunes. Yeah.
But you were telling me that you're doing good work in that we only know of about 10,000 stars that have been spectroscopically measured with the precision that this telescope and your spectrograph is capable of doing for the bright F, G, and K stars. Is that correct?
Stars have been measured more than 10,000, but what I meant is that only about 10,000 have been analyzed to the extent that we do here.
Right.
Because when you get the spectra, you have all the data, right? You
Right.
have all the optical spectra, you have everything from all the elements, the temperatures, the surface gravity that you can do. You have that. But not all of those spectra have been analyzed fully. Some people are interested only in oxygen, so they do only oxygen and they forget that spectra. So some stars only have oxygen abundances, or only carbon, or only iron, or some elements that are interested to specific projects. What we do here is we take a look at the whole range of elements, and not a lot of stars have that full composition analysis, starting with lithium at one end and ending at barium or other elements at the high end.
But a lot of the stars that you're observing, you're not even sure they have or harbor planets.
Yes.
So you're looking eventually for a predictive way to say this star has these chemical abundances, it's most likely to harbor gas giants, or it's a lower metallicity, it's probably only going to have rocky planets, which is astrobiologically interesting. But there's still a debate in astrobiology whether or not Jupiter was necessary for clearing out a lot of debris from the solar system so that we could have a stable orbit.
Yeah.
That's still debated. If you go the other way, right? We were discussing this. If you produce if a star has so much iron that it produces a lot of gas giants, it perhaps might create a solar system with so many gas giants that it could be orbitally chaotic, to the extent that it wouldn't offer an inner solar system the time or the stable orbits that it would need to develop life as we know it, correct?
Yeah.
Not to put words in your mouth.
So we don't even know how our system forms, so it's very difficult to say anything about other systems. Our system, if you take a look at our system, it looks kind of unique. For example, we found a lot of gas giants orbiting very close to their stars that we don't have in our solar system.
The hot Jupiters.
Hot Jupiters, for example, very close, like days around their stars.
Right.
That's very unusual compared to our solar system. We found very big planets very far away from their stars. Behind the orbit of Pluto, for example. That's as well very unusual. So we cannot see for sure how our system formed, and it's I think that's a question for future generations to answer, that if gas giants have any influence on a smaller planet formation. It might have, but it's difficult to say at the moment.
And this is we're at the Moletai, I'm not sure if I can pronounce it. Moletai
Yes.
Telescope. In English it looks like Moletai because Moletai. It's a new telescope, relatively, only 3 decades old.
30 years something.
30 years old, and a very new state-of-the-art spectrograph. So how much longer is this survey going to continue?
This survey will continue until we don't have people to work on it, or until the telescope breaks. This is one of the, or until someone else makes the discovery and it becomes unnecessary. But this is a long-term project, a long-term survey, and we plan it to keep doing that for foreseeable future.
Well, good luck to you. Thank you for taking the time to
Thank you.
Bring me out here and show me this beautiful telescope in a beautiful setting on the about 70 kilometers northwest, northwest, what is it?
Northeast a little bit,
northeast of Vilnius. Okay, thank you so much, Arnas.
Thank you.